So let's see here. Ooh, that's not going to work at all. Okay. All right, so we finished off last time with this group problem. We did this group problem right here. And we didn't quite finish part D because we haven't talked about center points yet. We don't even know what they are. But we'll come back and do that later. The next part of this section of the notes is stuff we really already have learned. I have moved it up previously. So we know how to take our significant effects and build our model. So you've seen all of this before. The part that's new is right here. So when we think about building our model, as I mentioned before, so voltage was the response to that one group problem. So that was that y or y hat in a model. And I mentioned this x1, x2, and x3, those are the coded values, right? We put in -1 or +1 for the x. We can put in all sorts of different numbers between -1 and +1. So in this example, if you remember, the coded value for x1 corresponded to temperature of 22 and 32 degrees Fahrenheit. Probably Celsius, if we're talking room temperatures. So those are the coded values. If we wanted to run an experiment at, say, 30 degrees, and I wanted to predict what the voltage would be at 30 degrees, in order to use this model, I need to convert that 30 degrees here into a coded value, right? Right? Thank you. There we go. So this x1 is a coded value. It goes from -1 to +1. And if I say, if this is 30 degrees, then what is the coded value? So those of you who have had other classes with me recognize something like this being how we go through linear interpolation, right? So you could linearly interpolate to get the coded value for x1 at 30 degrees. So if we're linearly interpolating, we can think of, well, if x1, here's 22 degrees, and that corresponds to -1. Here's 32 degrees. That corresponds to +1. We could get the equation of that line, right? And we could use the equation of that line to come in here and say, okay, if we have 30 degrees, x1 equals something. So let's get the equation of that line. T equals what? Y equals mx plus b. You have 2 points, and I'm asking you to do the 7th grade algebra, 8th grade algebra, 6th grade math, I don't know. 2 points to get an equation of a line. So take a minute to do that. Intercept's always at 0, yes. Y-intercept when x equals 0, right? So even though I've drawn the axis there, the y-intercept is right there. Okay, everybody got it? What's the y-intercept? 27, thank you. And then we have the slope, the rise over the run. So everyone get that equation? At least it shouldn't be a mystery, right? This is just the equation we would use to linearly interpolate. So now if I asked you if the temperature is 30 degrees, we plug that into there. And we could crank out x1 0.6. So we would put 0.6 in our model for x1, and then have to figure out some setting for x3, and we could predict a value for the voltage at 30 degrees Celsius. So this is there any noise in this? Is there any noise in this right here? Who thinks there's noise in this? We're taking 22 degrees and we're coding it as -1. That's all we're doing, right? And we're taking 32 degrees and coding it as +1. There's no data associated with this. Does that make sense? This is like a transfer, it's just a mathematical transformation. So that's generally people think about this as a linear regression, something where we have noise, but this is just, you could think of it almost like a unit conversion. So there is no noise in this equation. It's going from coded units, degrees Celsius, to uncoded units. So it's a mathematical transformation, and that's it. Does that make sense? Okay, good. So that's kind of important. So this is just a linear interpolation of going from one set of units to another set of units, if you want to think about it that way, or just think about it as you're doing some math operation on this stuff to go from one set to another. But there certainly is noise in our data, and we have modeled it. Our model has smoothed out the noise, and we'll talk about that later. Okay, any questions about going from real units to coded values? Right? It's a very practical thing, so if later on, if we want to say x1 equals 0.6 is an optimum, we need to at least tell someone what temperature that really is so they can really run it. You can't go up to an operator and say, set x1 at 0.6. They won't know what you're talking about. Okay, so next topic. Is how do we test for curvature? So let's think about this. So here we have, let's just think about this with one variable. If we plotted the high and low values for x1, and we made a plot versus y, we have two data points, one right there, and we've been just drawing a line through there. We've been assuming that the relationship between these two is linear. Right? That's the most elaborate model we can fit between 2 points, is a line. And we've already had the question is, well, what if it's not linear, right? So that's a great question. We would need to do something about that. So if it's not linear, we would say, okay, it's curved. There's some curvature in between those 2 points. Something like that is happening. And we need to figure out how do we determine if this is the real thing happening or if a line is okay. Does everyone understand the problem we're trying to address? Okay, so it's got to involve then taking more data. We've got 2 points, these 2 points, this curve that's fit through them goes through them just like the line does. So we got to get some more data, and we got to think, where should we take data? I could take data right here. Anywhere in between here I could take data. But where would be, if if I'm trying to determine the difference between this line, this curve and this line, where would be the best place to take some more data? Yeah, Thomas.
The center.
The center, right. Right here. Why?
That's where the curvature is highest.
Yep. Okay, does everyone see that? Makes some sense? So we ought to take data here. And what Thomas said, which is right, is because that's where this difference is the greatest. So already we're concerned about that because we know there's noise in the experiment in the data we collect. So that's where the signal ought to be the greatest. So we should take some more data there. So then what are we going to do? We're going to set x1 at its middle value, and we're going to do some experiments, and we're going to get a few data points. So if we get the data points and they come out here, we would probably say, well, that falls out on the line. That linear model is okay, right? If we get data points, out here, then we'd say, ooh, that doesn't seem to be right if this linear model is okay. That seems to argue that there's curvature. If I get data points and it's like this, we're probably not going to know, right? So we have to compare our signal to our noise. So the last one had a lot of noise. So our signal is going to be, we're going to take some data points. If I average those together, and they're coming out here, the distance here is the signal. Does everyone buy that? So that would be the average of new data at the center. And this other part, the other side of our signal, would be, that's what our linear model would predict at the same location. Is everyone okay with those descriptions in words? The average of our new data points from our experiment at when we set x1 equals 0 and we measure y, those are those points. And this guy right here is the prediction of this linear model at x1 equals 0. Is everyone okay with that? Okay, so now let's think about this a little bit more. How would we calculate this? I've got this and this. I've got two numbers here. They're average of all the low values of x1, average of all the high values of x1. This point right here, is it in the middle between the two? If I average this and this, do I get that? Looks like it. You can probably prove it to yourself. So that ends up being the average of the factorial points, which are the corner points. So we can see this in one dimension. It works in 2 and 3 and 4 dimensions, that your linear model, to get your linear model prediction at the center, you just average all the corner points together. And it gets you that. Is everyone okay with that? So then, our statistical test, that means our signal here, I'll call this thing C. It's y bar of that new data minus what our linear model predicts, which would be y bar of the corner points. We've been calling them factorial points. That's the signal, right? I'll just give it like that. That's this distance. Is everyone okay with that? Okay, so now that value isn't going to be exactly 0. So we have to figure out, well, how big does that distance have to be before we say, we don't think this linear model is okay, we think the curvature model is happening, right? As this distance gets larger and larger, we more and more believe this curvature is happening and not the linear model. So what are we going to compare the signal to? How do we, when I say big or small, those are relative terms. When I say C is big or small, a curvature that's big means this signal is big compared to what? The noise. Great. So now, a signal to noise ratio, we're going to have C divided by the noise of that guy. Who can describe what C is in words? It's back to a case that we covered in chapter 6. What is it? Katie? It's a difference between two means, right? The average of the new data minus the average of the factorial data. So difference between two means is going to be SC squared over NC plus SF squared over NF. We've gone through that several times. And we're going to assume that the noise is the same at the center and at the corner point, which means I can drop those subscripts and I can pull that S out there. And if we're assuming the S is the same, we always denote that P to say it's a pooled standard deviation. We're going to take the noise estimates everywhere that we know them and put them all together because we're assuming they're the same. Yeah, Bob?
That N sub C represents the new data, correct?
Yes. Yep, great question. N sub C, that's the number of new data points taken at x1 equals 0, or x1 and x2 equals 0 at the center. And then this is the number of corner points. This is the same as it always is. It's our pooled standard deviation. But one thing to note is we're always going to use our best, we're always going to calculate our best estimate of SP. That's something that, flag this for this next exam. This is that's one of the, I guess, common errors that I see on that next exam. All right. Any questions on that? Does that make sense? This is just a statistical test on the difference between two means. It's the means of the new data taken at the center minus the average of all the corner points, which is what our linear model would predict at the center. Okay. So center points in one dimension, x1 equals 1, so that would be it. The center point would be, x1 equals 0, x2 equals 0, so I meant to say 0 there. The center point for 3 is, you said x1 is 0, x2 is 0, x3 is 0. You go do some new experiments and you get some new data at the center. So then we're going to compare all the new data points taken at that location with the average of all those corner points, which would be what our linear model predicts. So all of this stuff here is what we've just talked about. Let's look at this example. So here we've got a 2 to the square design. We've got x1, we've got x1, or excuse me, x2. We've got a full factorial. How many replicates did we do? 2. 2 replicates at each, 2 runs at each corner point. We can take that, we can calculate let's call it an average yield. We can also take that, we can calculate a variance at each location. Each one of these has 1 degree of freedom. Everyone okay with that for the corner points? Same old there. Then to do this test for curvature, we took 4 center points. So we went back in the lab, set the temperature at its middle value, this aqueous organic ratio at its middle value, calculated reaction yield for 4 experiments. We got an average of the center points. So this is Y bar of your center points. And we also got a variance of the center points in lots of digits. There's an error in this slide. So the degrees of freedom, n minus 1 is 3, right? I think it's corrected on your sheet, should be. Okay, you got 3 degrees of freedom there. Does everyone see that? Okay, so we're going to go through this, this calculation. We're going to find the signal-to-noise ratio. We're going to find C. We're going to divide it by the noise of that calculation. So C is the average of our center points, right? Minus the average of our corner points. Which are those guys? So I would take 68.4 plus 72.0. So that's Y bar of the factorial points, and that's what our linear model would predict at the center. That difference we're calling C. It's the signal for curvature. And then we need to divide by the noise in this guy, which is the difference between 2 means. What's n sub C? 4 data points. What's n sub F? How many data points at the corner? 8? Good. There we go. We're almost there. The only thing that we need now is our pooled variance and then our pooled standard deviation. So to get this, let's erase some stuff. We have 5 estimates of the noise, right? Which one do you think is the best one? Of those 5 numbers, if I said pick a number, what do you think the variance really is? Which number would you pick? The last one. That's right, because it has the most degrees of freedom into it, right? More data went into this number than these, so when we're going to pool these together, we ought to take that into account. We ought to weight this one more heavily than the others. The weighting factor is degrees of freedom. So our pooled variance is going to be 3 times 0.395833. That's crazy. That's the numerator. Denominator is the sum of all the degrees of freedom. So we have 4 plus 3 is 7. Is everyone okay with that? That's how we've been pooling all things. But this is the first time they haven't all been the same, right? And this is pretty typical. When we have center points, we generally have more replicates at the center because we're trying to get enough degrees of freedom in this curvature test that it has a decent power to detect curvature. So SP squared ends up being some value that's probably in our notes. 0.8411. It's easy to forget to take the square root of that. 0.9171. So that number goes in there. putting that all together, looks like in the notes I got a T of 5.297. That's pretty big, right? Signal to noise ratio over 5, or saying we're about 5 standard deviations away from the hypothesized mean that of 0. So we're doing this statistical test that we assume that there is no curvature until we prove it otherwise. So we need to compare that T with the T star. So one-sided or two-sided? What do you think? Two-sided, good. Curvature can be concave up, concave down. We don't know. Two-sided, so if alpha is 5%, our T is going to be 2.5%. How many degrees of freedom do we use to find our hurdle value for T? Someone said the magic number. 7. So think of how many degrees of freedom went into this noise. And so we have 7. So we had 3 at the center, 1 at each corner point. They all came together for 7 degrees of freedom in the noise right there. So 2.365. So what's the conclusion? Is curvature significant or not? Yes. We're further out in the tails than the cutoff value. We are certainly in that rejection region, so we reject the null hypothesis. If we wanted to formally write down, our null hypothesis is the mean of this curvature value is 0. Alternate is that it's not 0. All right, so this is the same test you've done all before. It's a difference between two means. It's that case where the variances is the same, so we pool the variances. So this is purely a Chapter 6 problem. The difference is that we have a few more places that we pool the variance from. The 4 corners plus the center point. Okay. No group problem here? Seems like that would be fun if we had one. Oh, yes, we do. Good. Here is some really good practical advice for running center points. And you can read through those at your leisure. I put those in here for your reference for the future. In your project, we might be talking about this stuff when you start going on your project and actually have to decide how many center points am I going to run, when am I going to run them, those kind of things. So all this stuff is real world stuff, and since your project is going to be a real world project, read through that for the project. So now, let's work on a group problem, the time we've all been waiting for. Pay no attention to that man behind the curtain in the cabinet. Again, it's a good practice to write down how many NF, how many factorial points you have run before you jump too far into any sort of calculation. Feel free to talk to people around you, compare notes, all those kinds of things. Yeah, John. What's that? Oh. Okay, so you ran 20 runs total, right? And so you have a replicated 16 were replicated. How many center points does it say? Yeah.
So it's 16
Oh,
factors.
yeah. I'm trying to read upside down. 16 factorial points, right? So you have 2 to the 3 with r equals 2, and then the other 4 were the center points. That's what that's getting at. So yes, NF is 16. All right. Okay. Yeah, fine. Sure. Oh, you got one already. All right, sure. All right. You guys getting this? Okay, our signal is 0.9, right? So we took data, and if we got a value that was exactly 0, we would know the linear model's okay. Or we would have no evidence to reject the linear model, said more precisely. But it's not 0, it's 0.9, and our question always is, well, is that big enough? It's not exact. Our new data aren't exactly on that line. Are they far enough away from the line that we can say, we don't believe the linear model is okay? So we compare the signal to the noise, and if this signal is 0.9, we have to think, well, what's the noise in that particular signal? It's a difference between two means, so we develop the noise in the difference between two means, and you end up getting 2.68. Anyone else get that? That's our signal-to-noise ratio. We need to compare it to a hurdle value. Two-sided, but we got to count up degrees of freedom. How many degrees of freedom do we have? What you got? 19 is one. So here are the 19 is one. Who else has an answer? 11. Anyone else have another number? Let's think. So we have two replicates at the corner points, right? We have 8 corner points. Good. So everyone, it looks like everyone's on the same page. So 8 corner points. Each corner point brings 1 degree of freedom to the party, right? And the center points bring 3. So 8 degrees of freedom at the corners, 3 degrees of freedom at the center. And then when we pool them together, we have 11 total. Good. 2.201. So the conclusion is what? Significant. That's weird. Chris. Yes. Yep. Our null hypothesis is that it's linear, so we're never going to prove it's exactly linear, but we can prove that it's not. Okay, anyone have a question on this? There should be a question maybe in your mind. Maybe not of what we've done, but... Pardon? How do you graph this? Okay, that's a question I was hoping you would ask. So now we've found that curvature is significant, right? What does that mean? It means that our linear model's not okay. We can't use it. So we don't use it at all. So that model that we would have developed before, by finding significant effects, that is no good. And we have proven it to be no good. So that's the bad news. And now we have to do some more work in order to get a good model. Right? So this says, don't use that linear model. It's no good. The only place it will predict things are at the corner points where you know what's there anyway. So I wouldn't use it anywhere. So now, if we have curvature, right? So we haven't figured out, well, what does the curvature look like? We have one data point for curvature at the center. So think about a surface, right? So if you have, x1 and x2, and above it you have y. You have the surface. Does the curvature look like a mountaintop, right? Is it a valley? Think of the surface that could be above this x1, x2 plane. Is it something that looks like this in the x1 direction? Is it something that looks like this in the x2 direction? Right? There's lots of ways that this curvature can look. Right? All we found is we found a point here, and we have one point on this surface right here, right? And then the corner points. So we have 3 points. We can make lots of different curvature shapes go through 3 points. Is everyone okay with that? Okay, so what we need then is more data. We need to find the pen that I just lost. And then we need to figure out, where'd that guy go? We need to find more data. We need to model the curvature. So let me see. I think hopefully I have something along those lines here. I wanted to show you something, but I can't. So we need to find more data points to model the curvature, and that's going to be kind of the next category of designs. So we're going to think of an entirely a new set of designs that are designed to add more points to what we've done to model that bit of curvature. So let's set that aside for now, and for this next exam and for the next, say, several weeks of class, if the linear model hasn't failed the curvature test, we'll use it. If the linear model fails and curvature is significant, all we know now is we need to do something else. And we'll learn that later in the class. That's something else. But for right now, we'll just say curvature is significant. We're not going to use the linear model. Our work's not done. We got to get more data. All right, any questions on the curvature test? Okay. The last topic of this section of notes has to do with blocking. So remember, yeah. Okay. Yes, curvature can be negative. It's just that your center points are below your model predicted value. It's if your center point values are below your model prediction, it's exactly the same. Your t is negative, and if it's further out on the left side of the tails, you're in the rejection region. So you just keep going through the calculations. They're handled exactly the same way. So now, blocking. The deal with blocking is we have some sources of variation, and we want to get rid of them. Right? So we did that paired t-test, right? Remember that? Where we had the different cars, and we paired them up, and we used those to block out a source of variation. We're going to flesh that out into doing that on a larger scale and block out more than just one source of variation. So this is why we do blocking. We call these things lurking variables or nuisance variables. They're things that are going to mess up our experiment. The key is we're not interested in really measuring them. Of our blocking variable. We're not trying to get a nice number for its effect. We're just trying to get rid of it. Okay, so that's what this is saying too. Both these things are saying that. All right, so then we'll talk about this one a little bit later. It's going to broaden the basis for our conclusions, and then increasing precision means we do this to reduce the noise. If we reduce the noise, then all our signal-to-noise ratios go up. Our results are more precise. We have a higher power to detect any given level of an effect. So that's why we do blocking, and I think we will call it a week there, and we'll talk more about the details of blocking come Monday. So have a good fall break. Yes? Pardon? Pardon? Okay, the exam will be over how much homework we've gotten through up until the exam, basically. All right, let's see the schedule here. So we have an exam scheduled Tuesday when you get back.